Okay, today in this lecture I'm going to talk about basic potential step experiment. Potential step experiment and what we can learn and how to understand how the response works. This is going to help us develop a picture, microscopic picture of what goes on in electrochemical cells under a lot of different conditions. So imagine we have a cell, which we're going to apply some potential to as a function of time. And we're going to start at one potential, we'll call that E1, and at time equals 0, we're going to step the potential to E2. And we want to know what is the current response for this experiment. And we're going to need to define some boundary conditions to understand this current response. So let's imagine E2 is very negative compared to E0. And that's E0 for the reaction O, and electrons goes to R. And this has some E0. So if this is very negative of E0, the redox couple, all species will be reduced to R at electrode surface. Okay, so this is for E2. So when we make this step, we step to where we're very negative, and we're going to drive this reaction forward. Okay, so that's going to be one of our conditions. And imagine that we start with so we have a solution of O in an electrochemical cell, and E1 is going to be under conditions where no reduction occurs. So E is much greater than E0, more positive, and then E is much more negative than E0. And if you remember on the Texas Convention, this is a positive potential to the left and negative potential to the right. So we're stepping the potential more reduced. And the question is, what will the response of such an experiment provide for us? So let's think about it. So what's going to happen at time equals 0? So let's look at now the current response. And in order to calculate the current response, we need to know what? We need to think about if I have an electrode, say I have an electrode in my cell, counter electrode, my reference electrode, and my electrolyte, and this is unstirred. It's another important point in how this potential step experiment is set up. We're not stirring the electrolyte, so it's stagnant. So the only mass transfer is via diffusion. Well, how do I calculate the rate of electron transfer? Well, what I need to know the concentration of O at the electrode surface, x equals 0, as a function of time. This is what I want, because then I can write a first order rate equation that relates the current or the flux, in this case the rate of the reaction, equal to some forward rate constant times CO 0 T. And what we're going to do in this experiment is this forward rate is going to be assumed to be diffusion controlled because this rate constant is going to be very large. So I need to know this concentration at the electrode surface. So qualitatively, how do we think about that concentration changing as a function of time? Here's x, and this is going to be concentration of O. And at t equals 0, what's going to happen? Well, at t equals 0, time does go from negative to positive. That's not potential, that's time. I should say potential here is negative to positive, so we're stepping to a more reducing potential. That's what I meant to write. So as t continues in time, for negative time, the concentration is going to be determined simply by the bulk concentration in the solution, because there's no reaction occurring. So I can write that. It's going to be T equals 0. And this is going to be CO star, right? So everything's in equilibrium when we start the reaction, or when we start the experiment. Now, what happens at later times? So at some time later, I'm stepping the potential very negative. So what reaction is driven at the electrode surface? Well, if you have a very negative potential, your electrons are very reducing, they're very reactive. So this reaction is driven forward to make R. So that's going to consume O. And in fact, our boundary condition, this is at the electrode surface at x equals 0. Our boundary condition is in fact going to be set by having 0 concentration of O at the electrode surface. We'll call that CO 0T. That's always going to be 0 because we're applying such a reducing potential. And then how is the concentration going to change as we go into the bulk? Well, way in the bulk, we're of course still going to have the bulk concentration because you're not going to consume all the O in a very short period of time. And there's going to be some gradient going to that bulk concentration. So this might be at time T1. Now imagine we continue to run the experiment. What will happen at longer times? Well, the reaction will continue to occur. Notice there's a concentration gradient driving flux of CO towards the electrode surface. R is being generated and diffusing away from the electrode surface, but we're not plotting R in this plot yet. And so at longer times, the fusion layer will continue to grow in width, moving away from the electrode surface. So if we know that the current is diffusion limited, so I is diffusion limited, and this, we know this because we applied a very large negative potential so that all the O that makes it to the surface is immediately reduced to R. How do I think about the current response for this system? So in chapter 1, we thought about the current response in a related system where we stirred and we had a fixed stagnant layer thickness. In this case, the stagnant layer thickness is changing with time, but we can still think about the same concepts governing the current response of the system. So think about this for a second. What tells you the current you have to be measuring here under these conditions? Well, you know that the O that comes to the electrode surface is all converted to R. So what does that tell you? Well, every O takes n electrons to make R. So the flux of O to the surface is actually going to be related to the current, right? So the current is going to be related to the flux of O coming to the surface at, so the flux at x equals 0 as a function of time. And of course, we know how to calculate flux from concentration profiles. We did that in the last lecture. That's simply the diffusion flux, which is given by Fick's first law. Okay, so let's go through that now in a little more detail. So, current for purely diffusion limited reaction is given by slope of C of x, in this case CO of x, which is equal to J O x equals 0 equals negative diffusion coefficient of O times dC of x equals 0 dx. So it's the slope right here at the electrode surface. Okay, and that's going to tell us the flux of O. So what's going to happen as a function of time? So if I plot the current from this system as a function of time, when's the current the largest? Well, at time equals 0, what is the slope going to look like? Imagine I immediately set the surface potential of the electrode such that the surface concentration of O is 0. All the R that was there is immediately reduced to, O that is there is immediately reduced to R. Well, I'm going to have essentially a step function in concentration. So in fact, the slope, in principle, will be infinite. So the formal solution will find the current will actually go to infinity at time equals 0. And as time progresses, the current decays. And for long enough times, this concentration profile will get so shallow that the current will go to zero. Okay? So this is the expected response, qualitatively, that we can understand very simply with our microscopic picture of the system. So let's keep going through this. So this is section 5.2.1 in Bard and Faulkner. So in section 5.2.1, we're going to assume two things to get a more rigorous answer. One, we're going to assume you have a planar electrode, and that planar electrode is large relative to size of diffusion layer, to thickness, I should say, of diffusion layer. And we do that so we can consider diffusion only in one dimension moving away from the electrode. We don't have to consider three-dimensional diffusion, at least not yet. And the second assumption is that we have an unstirred solution. So what that means is, of course, mass transport is only by diffusion, so no convection. In a real cell, of course, there will always be some convection due to, for example, thermal gradients, which change the relative density of the electrolyte and cause motion in liquids. But those typically happen on a long length scale, where this assumption holds very well for short length scales on laboratory timescales. And we're going to do this reaction, O plus n electrons going to R. We know that no matter what kinetics are, so the kinetics might be very slow or they might be very fast, we can choose potential E2 such that reaction kinetics are fast because we have a large overpotential, right? We can choose a potential that gives us a very large overpotential that drives the reaction kinetics. You can think about that in the context of the Butler-Volmer equation, which we have derived in previous lectures and used now several times. And this will always create the situation where CO at x equals 0 as a function of time equals 0. So that's going to be one of our boundary conditions. Now the key to doing this, and we're not going to go through all the mathematical details, but we'll just set up the problem, is we have this diffusion equation, which we derived in class last time from Fick's first law, which we also did a derivation of. Okay, so this is the diffusion equation. This is Fick's second law, or the diffusion equation. And so what we want to do is, our goal is to solve this equation with boundary conditions to find COx of t. That's what we want to find. And then we can take flux at position 0t is going to be equal to I of t over NFA, right? So this is just converting a chemical flux into a current, assuming an electron reduction. This is the area of the electrode. This is Faraday's constant. This is x equals 0, right? This is x. So the flux is related to the current in this diffusion-controlled experiment. In fact, the flux is always related to the current because you can't consume or make species without other types of chemical reactions. And this is just going to be given by d0, dC, dO, diffusion coefficient of O times the derivative of the concentration of x and t dx at x equals 0. So this is kind of what we showed before. And so our boundary conditions, we need boundary conditions to solve this problem. And our boundary conditions are CO x of 0 equals what? What should we set the concentration of O to be at time equals 0 for all x? Well, remember what our potential step looked like. This is potential positive, negative, E1, step very negative, E2, And if we're very positive, we're essentially going to have all O, no R present at all. So I can just set this to CO star, right? So the concentration profile as a function of distance at time equals 0. Okay, so that's one of our boundary conditions. And our other boundary condition, or one of our other boundary conditions, has to do with the surface concentration. So at x equals 0, for all time greater than 0, for time greater than 0, what's the surface concentration going to be? Well, at the surface, I'm applying this very reducing potential, and if I have that very reducing potential, what do I expect the electrochemical reaction to be? Well, I'm going to take all the O present, make it into R, so this should reduce to 0. Okay, and I need one more boundary condition, and I need to think about what happens at the electrode surface, and then what happens very far away from the electrode surface. So if I'm sufficiently far away from the electrode surface, say I'm infinitely far away from the electrode surface, we call that a semi-infinite boundary condition. We say that the concentration is CO star, very far from the electrode surface, and how I do that mathematically is I say the limit of x goes to infinity of CO x of t is simply CO star. So these are 3 boundary conditions that I need for solving this problem. And this is called semi-infinite, and it's a semi-infinite boundary condition because it's infinite only in one direction. We start at x equals 0, and we're defining a boundary condition at infinity in, for example, the positive x direction. So far away from the electrode, nothing changes. And so we could go through the math to solve this diffusion equation. It requires use of the Laplace transform, which is sort of like a Fourier transform, if you remember that sort of math. It's not complicated, but it will take a while, so we're going to skip it. In this class, the solution is in the appendix of Bard and Faulkner. It goes through the derivation nicely if you're interested in the math. So we use so-called Laplace transform and get the concentration profile, so you have x and t, and then once we have this, we can figure out the current from the relationship between flux and current, and noting that the flux is given by the derivative of the concentration gradient at x equals 0, and this is called the Cottrell equation, and has this form, and the number of electrons in the electrochemical reduction reaction, O plus n electrons goes to R, F Faraday's constant, A the area of the electrode, diffusion coefficient to the 1/2 of the species, the bulk concentration, it's linear in bulk concentration, pi to the 1/2 time to the 1/2. And you'll notice I is proportional t to the negative 1/2, and this is indicative of diffusion control. So whenever you do something, any type of experiment, and your result is that the response decays as t to the 1/2, that tells you that likely whatever controls that response is controlled by diffusion. And that's because it takes longer and longer and longer for things to diffuse from further and further away. So let's explore this a little bit. So we note I dies off as t to the 1/2, or I could say a rate of t to the negative 1/2. And we note that this is a signature of diffusion controlled process. So note that it depends on d to the 1/2 and A. If you know A, you control CO star, that's just the amount of O you put in the electrolyte, you can measure D, which is very useful, right? You can measure the diffusion coefficient, or alternatively, if you know D, measure A. So So why would measuring A be useful in this manner? Of course, you can always measure the electrode surface area simply by taking a picture of it, using a ruler, etc. But what's useful here, if you think about an electrode, let's think about a spherical electrode with radius r, a planar electrode, planar circular electrode. It's embedded in some insulator, right? Like you might use in lab, okay? And at its surface, when you look at it with your eye, it might look flat, but there might be lots of roughness on that electrode. Label that roughness. So the microscopic surface area is not going to be equal to the surface area that you measure with, for example, an optical microscope or a scanner or a photograph. We call this the geometric area. That's what you measure using simple optical techniques. And we call this the microscopic area, surface area. And we also define something called a roughness factor. And the roughness factor is defined by the microscopic area divided by the geometric area. Okay? And you can see that it's simply the ratio of how much area you have in a microscopic sense, how much area in all those hills and valleys, compared to the area of an equivalently smooth, flat, planar surface. Okay, so how do you measure these areas? And this will bring us back to the Cottrell equation in a second, at least thinking about it. So how to measure. So one way, which you have done now in lab and you're analyzing the data, is to look at surface confined reaction. So for example, I can take platinum plus an electron plus a proton, and this is a platinum surface site, and I can make a platinum hydride. This is a surface reaction. So this is platinum on surface of metal. So this would be a platinum atom. And I can quantify this reaction. In fact, I can measure it very nicely. If I take a voltammogram, and I can plot this as E versus, say, the standard hydrogen electrode. This is current. And if I do this in the IUPAC nomenclature, which I like, positive, negative here, positive current, negative current here. As I sweep negative, at some point I'll start driving this reaction. It turns out I'll get some peaks. And these peaks are associated with driving this reaction on different facets of the platinum surface. And then I'll start making hydrogen. And this will be, for example, 2H plus 2 electrons going to H2. And this is the hydride reaction. And if I sweep back the other direction, I'll see some peaks that are platinum hydride oxidation. Right? I drive this reaction backwards, extract the electrons that I put in, and this is platinum hydride formation. So I can actually go, and in any modern electrochemical software, I can go and get the area of these peaks and integrate that and get Q, total charge, in coulombs in this integral. In order to integrate it, you can either use the built-in algorithm in the software you're using, or you can convert this to a current versus time trace, and current times time is simply charge in coulombs. And notice that I did not count in this integral this part. And the reason I didn't count this part is this is non-Faradaic background current. And that's a capacitive current, right? So that's a capacitive current. Okay, so I can do that. And then if I know, for example, if you know, this is what you do in lab, that platinum has, say, approximately 200 microcoulombs per centimeter squared, of platinum hydride formation current, then you can calculate the total charge in coulombs, divide by this factor, and get the area of the electrode. And you can practice that in the lab. Okay, let's go back to the Cottrell equation and think about how this microscopic surface area affects what you measure by a potential step experiment. So in the Cottrell potential step, how do we figure out what is the right area to use in the expression that we derived? Is it the microscopic area or is it the geometric area? What do you guys think? When should I use the microscopic area? When should I use the geometric area? Let's think about this. And so the answer that perhaps you came up with is it depends. And what do you think it depends on? Well, it depends on the time scale. So let's imagine, let's do a thought experiment. Imagine I have a rough surface, and just to make this, this is X. This is my surface of my electrode. And I start consuming some species, consuming some O to make R. And I think, how is the concentration profile going to develop? So I could write contours in concentration as lines, much like you would on a topography map. And originally, at short times, right, I'm going to consume O from near electrode at short t, right? So this is going to trace the microscopic area of my electrode. And if I keep pulling from the electrolyte, eventually these microscopic features are going to be blurred out by the overlapping diffusion fields coming from these sharp microscopic features. So at long t, microscopic features don't matter, right? And they don't matter, if you think about it, because if you're far away from the electrode surface, you don't care that there's this microscopic geometry, because the whole surface is acting as a boundary condition, and the whole surface is consuming O only as fast as it can diffuse from far away. And it doesn't matter if there's more surface area down here, you still have to pull from the same volume element of electrolyte, your O, to turn into R. At very short times, you actually have more electrolyte that's close to the surface, and you can actually pull more O. Okay, so we can actually understand something about the surface area and how that is affects our Cottrell experiment by just thinking through this. So keep that in mind. So let's go through this a little bit more rigorously. So if I had solved the differential equation to get the concentration profile, I would have found the following. To diffusion equation, I would have got the answer COXT is equal to CO star times the error function, I'll define that in a minute, of X over 2 diffusion coefficient of O dt to the 1/2. Okay, so what is the error function? Well, the error function is defined as follows. Error function of x. So if x is a variable, the error function of x would be defined by 2 over the square root of pi, integral from 0 to x, e to negative t squared dt. So the error function comes about from integrating Gaussians. Okay. So this is the error function, this is the definition. So that's just a simpler way to write this expression by use of the error function instead of writing out these integrals and defining all the parameters. So if we plot now CO over CO star as a function of x for different times, we go from 1 to 0. in that ratio. So at time equals 0, of course, we have same concentration everywhere. And the error function, and you can plot this in Mathematica, will give you a solution that looks like this. So T increases as you go down here, these curves. So if you look at x equals 2 d0t to the 1/2, okay, so if you have this term, x equals this value, right? Then we have the error function of 1, and that equals 0.84. So one way to interpret this is just giving you a mathematical interpretation. At a distance of 2 d0t to the 1/2, so at this distance, okay, c of xt over co star equals 0.84. So the concentration reaches 0.84 of the concentration in the bulk. So you've recovered most of the way to the bulk concentration once you get this distance away from the electrode. And so we call this distance, typically this distance is either 2 times the square root of dot, or just dot, dt to the 1/2, the square root of dt. This is called the diffusion length. And it's sort of how far in a diffusion problem species O can move given some time t. So for any given time, if you know the diffusion coefficient, you can kind of estimate how much of the solution will be depleted. Because by the time you get this far away, you've recovered most to your bulk concentration. So let's do an example here. So let's imagine dO is 1 times 10 to the negative 5 centimeters squared per second. And this is common for species in solution, for molecules. Okay. So if we can use this we can use this diffusion coefficient to calculate now, based on this diffusion length, about how much of the electrolyte will be depleted. So if t equals 1 microsecond, t equals 1 millisecond, or t equals 1 second. And we can calculate 2 dot to the 1/2. And we find that it's about 60 nanometers. Okay, so in 1 microsecond, you've depleted 60 nanometers away from your surface. So all your roughness that you can see by your that you can't see by eye is going to be smaller than this. So that all happens on a time scale of about 1 microsecond, which is quite fast in electrochemistry. 2 microns in a millisecond, 16 microns in a second. So by a second, you're actually already pretty far, pulling stuff pretty far from the electrode surface. This is fractions of a millimeter, right? So this is 100 microns is a tenth of a millimeter. So in a few seconds, in 10 seconds, 20 seconds, you've pulled stuff out at almost a millimeter of the electrolyte. And of course, this whole approach breaks down when you get those longer time scales, because you start having these convective currents that make the boundary conditions no longer true. Okay, so let's think about this now when we shrink the dimension of the electrode down very small. And you'll see why this is important in a second. We can use something called an ultra-micro electrode. These are very useful in analytical electrochemistry. So we have Cottrell potential step on ultra-micro electrode. And I might have a wire, a very small platinum wire, that I have embedded in glass or epoxy, okay? You can buy these now. You can also make them very small. People can make them as small as 10 nanometers, and the diameter of this might be 1 to 10 microns. Or if you make it as small as 10 nanometers. Those are difficult to make, it requires some expertise. Now, what assumption that we made in deriving the Cottrell equation doesn't hold under these conditions? Well, if I have such a small electrode, right, here's my electrode, here's my insulator, and I start pulling species, I start driving a reaction, O goes to R, what's the diffusion profile going to look like? What's the concentration gradient going to look like? Well, I'm initially going to pull stuff very close to the surface, but as time goes on, very quickly, I'm going to start pulling stuff now not in 1 dimension, but in 3 dimensions, right? So as time goes on, I'm going to pull stuff from further and further away from the electrode, but I'm going to be able to do it in 3 dimensions, not just in 1 dimension, and that's going to have big implications in the current. So for a long time, the electrode looks like a point sink of O. So O is basically diffusing to a point, and that's going to solve the diffusion, that's going to simplify the diffusion equation a lot. And so to solve this, again, we won't go through the math. We have to write fixed second law in spherical coordinates, which we can do. Now writing this concentration of O as a function of R plus 2 over R dCO RT dr. So this is just the same diffusion equation, but in spherical coordinates. And this just comes from the Laplacian operator del squared in spherical coordinates. Okay, so this, you've taken multivariate calculus, you've done this sort of stuff before. And then we can write the same boundary conditions, right? So we can write the same boundary conditions. Initial condition CO R of 0 equals CO star, of course, at time equals 0 for any position R, right, away from the electrode, we have the bulk concentration. Now I'm doing this spherically symmetric, so it's looking like a point source, so I'm only considering the variable R as I move away in 3 dimensions from my point sink or point source of species. And we can write the limit of R goes to infinity of C O R T. What's that going to be equal to? If I go very far away, what's CO going to be? Well, that's also going to be CO star, right? Because I'm far away, I haven't perturbed that. And the surface condition, CO R equals 0 as a function of time, is always going to be 0 for t is greater than 0. So that's just saying that I'm consuming all the R at the electrode surface for R equals 0. So if I go way back to the electrode surface, remember that we're considering this a point. And the solution to this equation, to these boundary conditions, the solution is given by I, Cottrell solution, assuming this potential step, equals NFA DO CO star 1 over pi DOT to the 1/2 plus 1 over R naught. Where in this case, this is the radius of our electrode. So we're assuming it has some radius, which actually affects this boundary condition, so R is greater than R naught. Okay? So we have a very small electrode with radius R naught. And now the current depends on 2 things. We can write this current, I d of t equals id linear, which is the previous solution to Cottrell equation, plus a constant part, which is NFA DO CO star over R naught. And this is a constant, right? R naught, CO, DO, these are all constants. They don't depend on time. So this is kind of nice. So what happens here as t goes to infinity? So if t goes to infinity, for this electrode, as t goes to infinity, I, diffusion current, goes to what? Well, it goes to this term, right? Because the linear term, t goes to infinity, the linear term goes away. So that's really interesting. So if you go to infinite time for a microelectrode, you actually get a constant current. And that's precisely because, if you think about it, there's a competition between pulling species from further and further away of the electrode with longer and longer time, with the fact that you have actually more volume to pull species from. So if I think about my electrode, right, and I'm pulling stuff from some element dr, in short time, I only have this volume element with this dr to pull species from, but the same dr at longer times gives me many more species to collect, but they have to diffuse further. So those two effects exactly compensate for each other and give rise to this constant current. So it's easy to get diffusion coefficients using microelectrodes. And you can't see this for a large electrode. In principle, you'd be able to see it for a large electrode if you just waited long enough, a normal electrode. But convection currents disrupt the boundary conditions, and in practice, you cannot do that. Okay, so we're almost done. So let's think about some applications of these microelectrodes. Okay, applications of microelectrodes. So let's consider what potentiostat does. So if I have an electrode, surface, here's the surface of the electrode, right? And I apply potential, say I apply a positive potential. I set up a double layer. This is the electrode. This is the electrolyte. I set up a double layer. But it takes some time to set up that double layer, because we have to actually charge that capacitor. And if you remember from some of the early lectures, the charge on this capacitor Q is equal to E, the potential step. This is the magnitude of potential step. So we derived this in chapter 1. Times double layer capacitance, CD, times 1 minus E to negative T over RSCD, where we call tau equals RSCD. This is the time constant. RC time constant, we typically call this. RC time constant. So if T is much, much smaller than tau, Q equals 0, right? So if T is much, much smaller than tau, right? This term goes to 0. This term up here goes to 0, right? T is very small. And E to the 0 is 1. 1 minus 1 is 0, so no charge on the electrode. But if T is much, much greater than tau, Q equals ECD. And of course, this is the definition of capacitance, is the charge per potential, per volt. Coulombs per volt is the capacitance. Okay, so tau sort of tells you the time scale for putting charge on our capacitor. So in practice, just something you should consider when doing fast electrochemical experiments, you can't charge electrode faster than the time constant for your cell, tau. Okay, and CD, the capacitance of my electrode is equal to pi times R naught squared. So this is just the area of a circular disk electrode, the area of a disk electrode, times C D naught, and this is the capacitance per unit area. So C D naught is typically 10 to 50 microfarads per centimeter squared for most metals. So this is just basically defining the capacitance as a function of the area and the intrinsic capacitance. And then we need to think about what is Ru. So, or R, here, the series resistance. So we care about uncompensated series resistance, okay, Ru. And this can be derived, as done by Newman actually, I think in the 50s, as following, where you have the radius of your electrode, of your disk, you have the conductivity of electrolyte, 4 pi times the conductivity of the electrolyte times the radius, and x is the distance from electrode. So I can use this expression, right? If x is much, much greater than R naught, we get Ru equals 1 over 4 pi k R naught, okay? So if my counter electrode, or my reference electrode in this case, is much further away from the electrode than the radius of the electrode, which is usually the case, if it's more than a few radii away, I get this as the uncompensated series resistance. And I can calculate RUCD, the time constant for this cell, as just pi R naught squared CD naught, this equation here for the capacitance, right, times the uncompensated resistance, series resistance, 4 pi k R naught, cancel terms and get CD naught R naught over 4 kappa. And what you can see is this time constant, tau, so how fast you can do an experiment, can be made arbitrarily small by making your electrode very small. These are all constants. Of course, you also want very conductive electrolyte to minimize the uncompensated series resistance. So that's nice. So for fast experiments, say you want to measure something on a microsecond time scale, you can do that if you use a micro or nano electrode. Okay? But of course, you always want to experimentally verify the time constant for your cell and make sure what you're measuring is not the RC time constant of your cell, not affected by that, and truly the parameters you're interested in analyzing. And with that, we'll end the lecture on potential step experiments.